Hello students, let's discuss about some more applications of the PN junction diode. Out of that, the first one is photodiode. So let's understand this first of all. What do you mean by photodiode and how we can use this, or what is the working principle, construction and all this. So this is the circuit diagram for that. You can notice here we have a PN junction diode and this is a transparent capsule, so that the light radiation will fall on it, and because of that light radiation and it starts conducting, and you can notice here the positive terminal is connected to the negative terminal of the battery, P type. So what kind of connection is this? Reverse bias. That's obvious. This is the circuit symbol and this is the response of the particular circuit, or the graph you can call like. So now let's understand this. Of course this is a convex lens, so somewhere all these parallel rays are being converged at this point. That's it, nothing. Okay, so we are converging all these rays at this particular on this diode. So let's understand the circuit in detail now, and let's define the photodiode first of all. A photodiode is essentially a reverse biased PN junction diode which is designed to respond to light absorbed. So whatever the light falling on this or absorbing by this diode, it should respond, and that was the working definition of. If you look at the principle, which means on what fact or on what principle it works, a reverse biased PN junction diode has a reverse saturation current which is mainly due to the flow of the minority carriers, isn't it or not, in the case of reverse bias. If light is allowed to fall on such a reverse biased PN junction diode, additional electron hole pairs are generated in both P and N regions. It produces a very large change in minority carrier concentration and hence increases the reverse current through the diode. It is found that the current through the diode varies almost linearly with the light flux. Hence, light can be detected using a reverse biased PN junction diode known as photodiode. Very well known thing for us this, isn't it or not? Okay, if you look at the construction of this, that was the working principle which we have discussed until now, isn't it or not? Because let me tell you in brief again once, so that we can go for the construction. So when light falls on it, extra number of electron hole pairs will be generated here. That was the basic principle in one line if you want to speak, since because as it has been operating in a reverse bias condition, the current will be very low, isn't it or not, because only the minority carriers. But this light energy what we are actually using here will create more electron hole pairs, and thus we can get more amount of. So for what purpose we can use this here, as they have been already connected in reverse bias, almost theoretically in the reverse bias situation the current through the diode will be 0. So if there is any light radiation of any particular wavelength, isn't it or not, so it can't be always a visible, right? So if we have an electromagnetic radiation or light radiation, and if we use the photodiode, if we can notice a current through this, then obviously we can say that there is a radiation. So photodiode can be used to detect the light also. Are you getting the point here? So let's look at the construction here also. The photodiode will consist of a PN junction diode obviously, and this is the clear capsule, plastic capsule, which is nothing but, okay, if radiation falls on the one of the surfaces, you can see here across the junction, and then the process will start. Of course here we can use the lens, convex lens, in order to converge the rays here, light rays here. Are we clear with this, ma? Okay, right. The only use of this using the convex lens is to increase the activity, optical activity, that's it. Other than that nothing. Okay, so to make the photodiode activity more maximum, we are using this, because more the converging the rays it will be off. And all the sides of the remaining sides of this plastic capsule will be either painted black or enclosed in a metallic case. What is the reason for that? Because only this illuminated region alone will be left transparent, while all the remaining will be closed, because the light radiation which is actually falling on it should completely fall on it. It should not neither escape nor it should leave this. So that was the reason. So we are actually trapping the entire light which is falling on the PN junction diode and we are focusing to fall on it. So that was the reason here. Okay, and remember here the photodiode will be having a very small dimensions. That's what the reason why we are actually keeping it in a very small dark region, or you can call it as like a plastic capsule sheet. Are we clear with this? Right. So now first of all, when it is in dark condition, what do you mean by that? Let's understand the working. So that's what my intention is. So let's understand that when photodiode is kept under a dark condition and when reverse voltage is applied, a sufficient value of almost a constant current which is independent of the magnitude of the reverse bias will be obtained. That's obvious, because now dark condition refers to no light is actually falling. So minimum almost a constant of, that's we have already seen right in the reverse bias situation. That's it. Now this current is corresponds to the reverse saturation current due to the thermally generated minority carriers, and we can call that current to be like nothing but we can call it as dark current. Remember that. So the current corresponds to the thermal agitated minority charge carriers in the reverse bias is nothing but dark current, since because we have not started illuminating this. So at that particular situation I am speaking about, and we can call it as dark current because it flows only when no light is incident on it. And remember that this dark current is proportional to the concentration of minority carriers, which are nothing but holes in the case of N type and as well as electrons in the case of P type. I am speaking about the minority, don't confuse here, minority charge carriers. And we can represent this dark current to be as I suffix D. Are we clear with this? Okay, and anyway majority charge carriers are not allowed to cross the junction barrier under this reverse bias situation. That's obvious, right? Isn't it or not? Okay, right. When light is allowed to incident on the diode surface, additional electron hole pairs are formed. But since the concentration of majority carriers is much greater as compared to that of minority carriers, the percentage increase of majority carriers is much smaller than the percentage increase of minority carriers. Hence, we can neglect the increase in majority density and can consider the radiation entirely as minority carrier injector. These injected minority carriers diffuse to the junction, crosses the particular barrier and contribute to the additional current. Therefore, we can have a large reverse bias condition under this. The total reverse current which you can give it as IS plus ID, and of course I can call that to be a short circuited current when you incident the light. So the total current which will be nothing but here is IS plus ID, where IS is nothing but short circuit current. IS is. Are you getting the point here? And this short circuit current is proportional to the intensity. More the intensity, more it will be. But anyway, dark current is only proportional to the carrier concentration, whatever we are actually having, the minority. So for different intensities, this is what the response we can get. And now you can ask me that, sir, that's all fine, okay, but why we should operate this particular photodiode in the reverse bias situation only? Why can't we operate in the forward bias condition? Isn't it or not? Because in the forward bias condition, we know that the current will be in the order of milliampere, while in the reverse bias condition we are having microampere, right? So what must be the reason to operate the photodiodes in the reverse bias situation? That also we should consider, right? Okay, so let's understand that in detail. Suppose if you consider an N-type semiconductor, what are the majority charge carriers of the that semiconductor? Obviously electrons. Majority I am speaking about. For N-type, it's electrons, isn't it or not? Okay, and that electron density, which is nothing but the majority carrier density, is much larger than the minority hole density. Can I write like this? N-type and of course is far greater than holes. Let's say suppose N refers to the electrons, P refers to the holes. Can I call like? Can I call like this? Okay, ma? Right. Of course, where N refers to the electrons, while P refers to the holes. Remember that. Keep that in mind. When the light falls on the diode of certain reasonable frequency, then both the types of these carriers increases equally in number, isn't it or not? Both either the electrons and as well as the holes will keep on increase. Now at that particular instant of time, I am calling it as n dash equal to n plus delta n, change in that, because of this is the initial number, this is the increment, that was the total after light incident. Similarly p dash I can write it as p plus delta p. Can I write down? Can I write down or not? And remember that delta n will be always equal to delta p, equivalent number of, that's it, no? When an electron jumps out, that subsequently it gives us the hole. So delta n and delta p will be always equal. And already we know that n is far greater than p, isn't it or not, in the case of n-type semiconductor. Now what we can write down from this, delta n by n is much less than delta p by p, isn't it or not? And what do you mean by this delta n by n and delta p by b? Fractional increase. Therefore what we can call here, the fractional increase in majority carriers is much less than the fractional increase in minority carriers. Consequently what happens? The fractional change due to the photo effects on the minority carrier dominated reverse bias current and is more easily measurable than the fractional change in the majority carrier dominated forward bias current, isn't it or not? Hence photodiodes are preferable used in the reverse bias condition for measuring the light intensity. Are we getting the point here? So it is very easy for us to measure in this order of. Are we clear this? So that was the reason why we are actually operating the photodiode in reverse bias situation. Okay ma? And if you call the uses of this photodiode is used in the detection of optical signals, it can be used in the demodulation of optical signals and in the light operated switches, speed reading of computer punch cards, ID cards, computer punch cards we have, right? CP cards. So that was. And in electronic circuits, all these are we have this photodiodes. So to detect the light we can. Are we clear with this? Okay ma? Let's see one more. Light emitting diode, or simply you can call it as LED, the most commonly used diode, light emitting diode. In our day-to-day life we use them, right? So that was the working, construction, all that. So I hope you are all very familiar with all these LEDs. So we are going to discuss about the theoretical part of that. So how it will be actually constructed and all that we have this. Now let's understand that. So first of all, it's nothing but a forward biased PN junction diode, but of course it's a specially made. The reason is it can emit the visible light when energized. That's it, right? We are actually having different kinds of LEDs, right? Of course it need not to be always visible. We have IR LEDs also, which you can notice in the TV remotes. Just before the TV remote we can notice a white color bulb like structure, right? That LED is nothing but an IR LED. You can notice when you watch that, try to press the buttons of the remote and watch that LED when you are pressing through a camera. So open your phone camera and try to place the LED just before the camera lens, so that you have to see the LED in that camera screen. The moment when you press the buttons, you can see the LED is glowing. So that indicates that it is working. All the buttons are working or not, we can notice. If the buttons of the remote are working or not, we can verify by using this. If the moment when you press the button, if the LED glows, which means that particular button is actually working. If not so, that was. So even in that method also you can test the remote, and that light or the bulb you are actually watching is nothing but this LED IR, but that was because human eye cannot detect, right? That was. So now we have different colors of LEDs also which emits that. So now we will discuss about such a kind of one in the region of visible light. Okay, when a PN junction diode is forward biased, obviously we know that the potential barrier is lowered and the majority charge carriers start crossing the junction, isn't it or not? And as soon as the conduction band electrons from N region cross the barrier and enter the P region, they recombine with the holes. And similarly, some holes from the P region may try to cross the junction, but a conduction band electron may fall into hole before the hole crosses the junction because of the electric field which was developed there. In either of the case, a recombination of the electron and holes takes place. Now, since a definite amount of energy is required to generate an electron hole pair, the same energy is released when an electron recombines with the hole. If let's say suppose we can call Eg is the radiation corresponding to the emission of the wavelength, and we can give that wavelength can be given as lambda equal to Eg, that energy needed, or let me correct this properly. We can write it to be like lambda equal to Hc by Eg, Hc by Eg, where Eg is nothing but the energy which is nothing but radiation which corresponds to the emission of the wavelength, radiation of energy of the emitted wavelength or the light, whatever we are calling it as. So using the particular proper values of the energy, choosing that, we can have the respective wavelength, since Hc constant, right? So 12,400, all that you remember, right? So 12,400 by the energy which you can call it to be. So basing on choosing that value, we can design or we can select whatever the kind of the wavelength we are actually needed. So what that wavelength refers to? Color only, right? So that was in the visible refers to VIBGYO or VIBGR. So choosing on that respective energy, we can have the different colors: violet, indigo, blue, green, yellow, orange and red. And beyond the values also we can have, that was IR and of course UV. Are we clear with this? So by a proper choice of the band gap and the material, radiation of desired wavelength can be obtained. But mostly we will have always the orange, yellow and green. Okay, and if you consider for red or green light, gallium phosphide, if I am not wrong, gallium phosphide, GAP, gallium phosphide, that combination of that semiconductor diode will give us the red or green light. Are we clear with this? Now let's look about the construction of this. Here an n-type layer is grown and then a p-type layer is deposited on it, and of course by the process of the diffusion. You can notice here there are metal contacts. Have you seen here? These two are the metal contacts, either here one and this one. These are the metal contacts. Notice there they are only at the edges but not in the middle, because from there alone we will have the radiation which being emitted out. Okay, and they are at the outer edge alone of the p layer, so that the light will escape from this free surface, whatever it is. And now for making the cathode connections, metal film, here you can notice here a metal film will be coated at the bottom of this entire, and this film is also will be used for this purpose because it can reflect as much amount of the light which falls on this. So for that purpose alone we will have a coating here. So the moment when it when light will be, the energy radiation was falling coming out of there, so this film will reflect. Preferably we use for the gold here, and this kind you can notice here, such a kind of specially prepared PN junction, because it is not like the normal kind, right? So in normal PN junction diode we don't have all these metal frames or metal contacts and all. So such a kind of specially made PN junction diode is nothing but our LED. Are we clear with this? And of course you can notice here the light output, if you consider along the y-axis, and the forward current along the x-axis, and this was the nature of the graph. Okay, and most important I want to repeat is the color of the light emitted by an LED always depends on the band energy gap. You can notice here Eg. So choosing that we can have the color. Of course the wavelength, what I am speaking is the intensity of the light emitted is determined by the forward current conducted by the PN junction diode. That's why I have taken this graph. Forward current refers to light output milliwatt, you can notice here, right? And that was intensity of light. So more it will be more of. Are we clear with this? Okay, ma. And what are the advantages of LEDs over the regular kind of conventional incandescent lamps we are having? If you observe, so the most common answer what you know is power efficient, isn't or not? LEDs will consume less power when you compare with the regular kinds of. That was first one. And second one is let me write down uses, economical. That was first one, isn't it or not? Second one. Coming to the power consumption, which is okay. So low power consumes, and low operation voltage and less power consumption, as I told. So low operational voltage, isn't it or not? Even with the power banks also we are having the LED light bulbs which can operate with the power banks, the normal kind of, with even a 1 volt 5 volt battery also we have. With that also the LED will low, very powerful, isn't it or not? That was. And they have a fast action and no warm up time is required. Warm up time, no warm up time. Let me tell you what is this. Have you ever noticed the street lights is required? Have you ever noticed the street lights, this orange color, white color lights, sodium mercury lamps I'm speaking about? Ever noticed? In the evening, if not so, try to observe them. When they switched on, when they have been switched on, either the sodium lamp, which is nothing but the orange color I am speaking about, or the mercury, the white color one, the huge, like will be very huge. So the moment when they were switched on, you can notice there that both of them will glow with an increasing in intensity. The moment when they have been switched on, the light will never switches on automatically, which is like the moment when you switch it on, you are not going to get the pure white light and as well as this pure orange light. Did you notice ever? And that was, we call it as warm up time. For sodium vapor lamp and as well as mercury vapor lamp, the warm up time is required. While for LEDs, now in our Naveli township, we can see major of the street lights have been replaced with LEDs to reduce the power consumption. So there you can notice the moment when they have been switched on, the next second they'll glow. So no warm up time is required. The moment you apply the voltage, obviously it will be having. And one more is their bandwidth is very large, nearly, of course, and of course they will always emit monochromatic. So the light whatever we are actually getting here, it will be always monochromatic. That's it, right? Choosing the energy will give the particular wavelength. So almost you can treat the LED to be like a monochromatic. Almost you can treat it to be like. That's it. For every energy band gap you change, the wavelength will change, and that was obviously. Coming to one more thing, they are long life and they are sturdy enough. They have a long life. Not like the regular kind of the bulbs. LEDs will have a very long life. Okay. Coming to the last one, their fast on off action. On off action will be very, which means like if you notice the tube light and regular kind of the bulbs, for the rapid action they will blow out very quickly, but for LEDs you don't have that problem. Fast on off action, that's all for the uses in this case. Okay. And the infrared LEDs I told you already for the TV remotes, right? So such a kind of, if you use those IR radiation LEDs, they are actually the potential source for optical fiber communication. Later in the engineering of the higher levels you will understand what is this optical fiber communication and all. And anyway, in the ray optics you have this, you can notice this by using the phenomenon of total internal reflection. We can have this optical fiber communication. When light was incident at a particular angle greater than the critical angle, the light will undergo for the multiple reflections and will come out, and that was total internal reflection. Total internal reflection greater than the critical angle if the angle of incidence is more. So in ray optics you will get this. And coming to the last one, they are actually, instead of all the cathode ray tubes in the cathode ray, whatever the TVs and all we are having, that all the cathode ray tubes, earlier I am speaking about, earlier the size of the TVs was to be very huge, computer monitors and all was to be very huge, were noticed, but they were called cathode ray tubes, CRT monitors we call it, CRT monitors we call them as, those huge one. cathode ray tube. CRT refers to cathode ray tube. So those scintillations, whatever you are actually watching, and the color of that CRT monitors also used to be very dull. But now all these CRT monitors have been replaced with LED monitors. Now we are actually watching all them, right? That was OLED, QLED, all the different kinds of we are having, right, in the modern era, and that was the supreme models of all this. So increasing the pixel quality will obviously increases the quality of the picture. So that was the marketing strategy which is behind all this. Of course, marketing strategy and the size of the LEDs what they are actually using, and the frequency, radiations and all will make this all the modern era display equipments are more brighter, which are safer for the eye too. That was. Are we clear with this? In many display units also you might have seen all this. So indicator lamps, display lights, all these are many we have LED applications. So simply to say, in our modern day life, without an LED we don't have any of the electronic gadget. So that was the prominent place that got by LED. Even for the on off switch for the in any circuit also, an LED will be given for you. The moment when the LED glows, it clearly indicates that the circuit is having the power. So such a kind of, so that has been replaced like an indicator lamp for us, and that was I'm speaking about. So are we clear with this? Right. Let's see the next application, solar cell. We have already discussed about this in the photoelectric effect, which is nothing but the photovoltaic cell. So now again let's discuss about this. So a solar cell is nothing but it's a junction diode which converts solar energy into electricity, and of course it based on the photovoltaic effect. We have already seen this. Simply to say, generation of voltage due to bombardment of light photons. So it takes the light and that creates the voltage. You can see here it will be having a PN junction diode. Either it will be made up of silica pure intrinsic or an extrinsic gallium arsenide, GaAs, either intrinsic or extrinsic, both of, and a thin layer of p type is grown. You can notice here thin layer of p type is grown by the diffusion of a suitable acceptor impurity on an n type semiconductor. You can notice here, right? The top of the p layer is provided with few finger electrodes, and this leaves open enough space for the light to reach the thin p layer, and hence the underlying PN junction. The bottom of the N layer is provided with a current collecting electrode. You can see here the metal contact is nothing but that electrode. So when light falls on this, and of course you can see the glass protection over this. So when light falls on this, it actually creates that, and thus the temperature increases at the junction, and thus the movement of the charge carriers, and you can notice here we can get that. Okay, suppose if let's speak in detail about the working here also. It will be better for our understanding. When light photons with energy reaches the junction, they excite the electrons from the valence band to conduction band, and of course leaving what happens when the electrons leaves the valence band and enters the conduction band, they leave behind the holes. That's obvious, isn't it or not? Now these electron hole pairs generated in the depletion region move in opposite direction due to the barrier field, which you have already seen in junction diode, the working and all we have already seen. So the same working, see the working will be same for all the kinds of the devices, but the point is in what different kinds of the modes we are actually using. That's why we are actually discussing about all these in detail. Okay, and photo generated electrons move towards the n side and the holes towards the p side. The collection of these charge carriers make p side a positive electrode and n side a negative electrode, and thus we can have a photovoltage will be set up across this junction. When a load resistance is connected across, you can see here, when a load resistance is connected across in the external circuit, photocurrent will flows. And remember, this photocurrent is proportional to the intensity of illumination. More the light, more it will be. That's it. No, whenever the sunlight falls with a greater intensity, we can have the more voltage. The point what you have to understand here is, this is a cell which is nothing but a battery which creates a potential difference. So which stores, it has to be that storage is needed. That's the main disadvantage of this, so of the solar cell. and the intensity of the sunlight is much needed. More the intensity we have, obviously we can have the more kind of. And the more advantages of the solar cell are they are pollution free, and they are long lasting, and they are maintenance free. When once we install, even for the household purposes also, now in the modern days now we have, but earlier the cost of installation and all were actually very high cost of, but now even for the household also, even airports are being run with the solar power. Trivandrum is one of the example for that. So airports are being run on the solar cell. That was, and even in our navy also we have, right? So the solar power park. So that was the modern era use regarding the solar cell. Without the, so instead of the conventional energy sources like the thermal, nuclear and all this, so it's better to have like this kind of. That's it, right? They're we are using the naturally available solar energy, and that we are actually converting into the electrical energy. That's what more important here, the pollution free rate. Okay. And important criteria for this solar cell is most important thing is their conductivity and availability of the raw materials and the cost factor, because the manufacturing need a lot of it's more costly. So that was the only factor, but of course nowadays on a larger scale, because of the production, it's commercially viable too. So that was, now in modern days we have economical solar cells too, which can able to provide even solar cells having, which is nothing but a solar cell power banks also we are having, even for the mobiles. If you place them solar working on that solar cells, we have torchlights, we have power banks, and we have the even water filled water geysers, which are nothing but hot geysers also we have. So all they are we have. So even wristwatches also, hand calculators. I think do you all have that Casio scientific calculators, or even the regular kind of the calculators also? At the corner you will be having a brown color like thing, right? And that was a solar cell. So calculators will work on that. Wristwatches, some are there, and spacecrafts use the all the solar cells, which whatever the ISS works on the solar cells only. We don't have a power line from ground to the, from Earth to the solar ISS, right? International Space Station. So solar ISS or the satellites, they actually draw the power from the solar cell. Okay, are we clear with this? That was the regarding the solar cells and all. And of course, the if you plot a graph between output current and output voltage, this is what the graph. Have you seen this graph anywhere? Earlier we have plotted, right? The same kind of the graph. So the problem with the solar cells is the output voltage will be very small enough. So the devices has to be storages of this particular batteries, that was more needed. So on a large scale, if it was done, it was okay, but for small and all, the output voltage is a very smaller one. Optimum it can be. Nowadays, as I told you, right, the solar lamps also being, so LEDs are being connected to this solar cells. So as LEDs anyway, they use minimum optimum power, very less voltage. Solar cells are being very effectively used in that case. So that's all of your semiconductors and devices. Hope we have a very good detailed session regarding all the previous chapters too. So your physics syllabus, as far as this particular chapter is concerned, is finished. The remaining will be done by the remaining faculties. Are we clear with this so far? Thank you. Thank you very much.